Hello everyone and welcome to today's Chemistry Daily Booster. This is number 2 for our Paper 2 series. Do notice this is an advanced information listed topic and that is for both higher and foundation chemistry. What we're going to be looking at in our booster today are Group 7, the halogens. So these are the second column in from the right hand side of the periodic table, and remember you do get a periodic table in the exam, so there's no need to memorise their names. What we do need to know about the halogens though, first of all we need to know Group 7 is called the halogens, and one of the most important things here is the fact that the halogens are diatomic. That means they go around as a pair of atoms. So whenever you write a halogen on its own, you must always have that little 2 in the bottom right. If you forget that, you are not getting any marks on any balanced symbol equations that require a halogen. So not even the 1 mark, because the formulas will be wrong and your balancing will be wrong. Please remember, diatomic, little 2 in the bottom right, anytime you write a halogen. We also need to know these little kind of trends, if you like, in their states and their colours. What we find then, here are our 5 key halogens: fluorine, chlorine, bromine, iodine and astatine. At the top of our group, we find that they are gases. At the bottom of the group, they are solids. Bromine is the only liquid. So 2 gases, 1 liquid, 2 solids. As far as the colours go, it gets darker the further down we go. So we start off with fluorine is pale yellow, chlorine is a green gas, bromine is the orange liquid, iodine a grey solid, and astatine a dark grey or a black solid. They can ask you to fill out that table with these halogens and their key bits of information missing. So this is just one of those things I suggest stick it on a flashcard and then just test yourself. Fluorine, gas, pale yellow. Just make sure you do know them so that if that question comes up, dead easy to fill it in and get those marks. In terms of the properties of our halogens then, they are brittle when they're solid and they're poor electrical conductors. So pretty typical of our non-metals there. In terms of the trends or the patterns as we go down the group, as we've already said, they go gas, then liquid, then solid. So the further down we go, they transition from gases to solids. They get darker in colour. Their melting and boiling points increase and their density increases. Let's take a look at some of these reactions then. First one, Group 7 react with metals to produce a salt. We have got our general word equation here. Metal plus halogen makes the metal halide. Key thing when we're writing these word equations is if we've got a halogen on its own, it always ends in INE. So halogen on its own is INE. When it's joined to the metal as the salt, it must end in IDE. If you write something like sodium chlorine as the salt, you're not getting the mark. The ending is important, okay? So on its own, all halogens end in INE. When they're joined to a metal, they all end in IDE. So just go careful on that. We then come on to our balanced symbol equation, which we can see here. We've got sodium reacting with chlorine to make sodium chloride. This is where that diatomic bit is super important. If we just written that as Cl, then we just have Na plus Cl makes NaCl. It would seem like it was balanced. It is not, because chlorine exists as a diatomic molecule, Cl2. As soon as you put that in, we know we've got to have 2 sodiums and 2 sodium chlorides. Hence why if you don't remember that the halogens are diatomic, you're going to throw away marks on this paper. In terms of the reactivity of our halogens, as we go down the group, then the reactivity decreases. So the further down they go, the less reactive they become. Opposite to Group 1, the alkali metals. The reason is that as we go further down that group, we've got more shells before we get to the outer shell, and that means the outer shell electrons are further from the nucleus. What we're doing as far as group 7 goes though, is we need to gain an electron. So because we're trying to pull an electron in, if that outer shell is further from the nucleus, then we've got a weaker force of attraction, which makes it harder to gain the electron we need. Therefore, it's less reactive the further down we go. In terms of their chemical properties, then the reason they all react in a similar way is because they're all in group 7, therefore they all have 7 electrons in their outer shell. Remember that phrase anytime we're asked why do all of the elements in group or whatever react the same, because they all have however many electrons in the outer shell. Make sure you state the number of electrons and the phrase outer shell there. When they're actually undergoing a reaction, they gain a single electron in order to actually give us an ion that has a single negative charge. So we start off with our generic halogen here, X2. So X could be any of the symbols, so fluorine, F, chlorine, Cl, etc. But always the little 2 in the subscript position because they're always diatomic. Because we've got 2 of them, then we need 2 electrons, 1 for each of those halogen atoms, and we will make 2 of the halide ions. So just single minus charge. When we actually come on to what they've specified on the advanced information, then it's all about the reactivities in displacement reactions. Now, displacement reactions of the halogens are one of those experiments that you should have done in class. The key pattern is right here. In a displacement reaction, a more reactive halogen will displace the less reactive one from the halide, the salt basically. So what we're really seeing here, remember what we've said, reactivity is going to decrease as we go down the group. So as we go further down the group, reactivity decreases. That means at the top of the group where we've got fluorine, chlorine, bromine, okay, these are the 3 we're going to focus on in this case. So fluorine is the most reactive, chlorine in the middle, bromine the least reactive. If we've got a little scenario here where we've got chlorine and we've got a halide with bromine in it, then bromine is less reactive than chlorine. Therefore, what we find is our chlorine here is more reactive than our bromine. Therefore, what happens is bromine gets kicked out, chlorine then comes in and takes its place. So we make our sodium chloride and bromine because the more reactive halogen has displaced the less reactive one. In terms of the experiment you will have done for this, then you will have had a little spotting tile, which we can see down in this bottom corner here. And into that spotting tile, what we would have done is in our first row, so going across here, then we would have put a few drops of chlorine water. Second row, we'd have done bromine water, bottom row, iodine solution. Then what we've done is added to this first column here, we would have put a solution of sodium chloride. So a couple of drops of sodium chloride in each, and we'd have been looking for a colour change. Next row along, this one, then we'd have done our sodium bromide, and then we'd have done our sodium iodide. So what we can see is that based on if we get a change in colour or not, that tells us whether there is a reaction or not. So if we have a little look at our, let's have a look at the top row first of all then. Okay, so our top row here, this is all chlorine water that we've got. So chlorine is on its own. And remember, here is our chlorine. Put iodine in as well for us. So when we're looking at chlorine on its own, if it's more reactive than the halogen in the salt, it's going to take its place. So we should see a colour change. So in the top left, we had sodium chloride. There is no colour change, it just stays the same because chlorine and chloride is the same. There's going to be no difference. Our next one is going to be sodium bromide. Now bromine is less reactive than chlorine, therefore we can see there's that slight colour change. It's kind of a bit of a yellowy colour there. And then when we come to our third one along, that is our potassium iodide, and again iodine less reactive than chlorine, so we get a very clear colour change there. Now, what we tend to find is that you could actually just end up with a little table kind of plotted, and all they'll have done is basically put crosses if there's no reaction and ticks if there is a reaction. So based on this, or they could have used words, you would then have to place them in order of reactivity. So quite simply, the ones that displace the most are the most reactive, working your way down to the ones that displaced either nothing or only one thing, least reactive. If you're doing higher tier, then you do need to know about half equations, because again, half equations, going back to our first chemistry paper, are used to model what happens to an individual reactant in a particular reaction. So in this case, what we're looking at is if we've got our chlorine and then we're reacting it with something like our sodium bromide. What we have, looking at chlorine first of all, we start off with chlorine Cl2. We are then going to have 1 electron gained by each chlorine atom, so we need 2 electrons, and we're going to make 2 chloride ions, Cl-. Because they are gaining an electron, then we have got a reduction. Remember oil rig, reduction is the gain of electrons. If we look at the other half equation, focusing on our bromine, okay, we start off with bromide ions, 2 of them. We're going to make bromine, Br2, and we're also going to have our 2 electrons that were on our bromide ions that we've now released. Because of that, it is an oxidation, because oxidation is the loss of electrons. These two are happening together, therefore it is a redox reaction. We have both reduction and oxidation together, which if we put them into one ionic equation, ignoring the spectators because they're not involved in the reaction, Cl2 plus 2Br- makes 2Cl- plus Br2. As always, if there are some bits on here that you want to go into a little bit more detail, go over just one more time, you can use the video on the main channel. You've also hopefully got your revision guides, your classwork, and have a look at some of the past exam papers to see the style of questions that comes up. Don't forget to join us again tomorrow for our next Chemistry Daily Booster.